the other two problems that we had, one was message integrity and authentication. And what we will do is we'll start with authentication and then we'll go to integrity. Okay? So let's start with authentication. And the way we'll do it is we'll try to build our own authentication protocol. And let's see how we can do it. So let's start with trying to develop our protocol where we say, okay, how can Alice confirm to Bob that it's really Alice? And nobody else should be able to come in and pretend to be Alice. So, so when we start with something, and you're trying to, even for your research or whatever, you're trying to develop a protocol, always start with the simplest case, right? And then slowly build it up so that it covers whatever problems you can find with your simple solution. So in the simplest case, Alice can just come and say, I am Alice. And what could go wrong? And if Bob gets a message, so in this protocol, if somebody comes and says, I'm Alice, Bob says, okay, you're Alice, and you're not. Of course, this is not a good protocol because Trudy can simply declare the same thing, right? Trudy can also say, I'm Alice. It's not like Bob is sitting and looking at Alice's face, it's over the network, so you don't know who is claiming to be Alice. Other thing you could say, okay, let's look at something else. Somebody is saying that she is Alice. Let's look at the IP address that she's coming from. And if somehow I know what is Alice's IP address, then I will say, okay, a message is coming saying it's Alice, and it's coming from an address which I know is Alice's address. It's okay. But then the problem is, Trudy can also create a packet with a spoofed IP address. So I can put any IP address that I want. Right? Bob doesn't know. Did it really come from this IP address or just especially with Linux, you can go into the kernel and in the code, and you can hack into it and you can send out IP packets with whatever address you want. Not very difficult to do it. Right? So this doesn't work either. What you could say is, all right, fine, since people can pick up on IP addresses, let's have a secret password, a password of some kind, which Alice and Bob share. So now Alice can send a message saying, I'm Alice, has the address and the password. But this doesn't work because of what is something called a playback attack. Right? Trudy can record this packet, or copy the packet, and send the same packet again. So Bob gets a message saying, I'm Alice, it has the password he's looking for, and it has the IP address. The problem is, this is in plain text, encrypted. Doesn't make any difference, right? Even if it is encrypted password, I can record the same thing and send it. Bob will decrypt it. So that doesn't work either. So the main thing with authentication really is, if people are observing, you want to prevent them from pretending to be the same person again, right? So you don't want people to use credentials that they have observed. So it's like, you're trying to withdraw money, I'll look and see what's your PIN number or whatever, right? You try to reuse that. Or you're trying to log in somewhere, and I see what's your password. Later on, I log in using that password. Right? You don't want that to happen. So what's the option? So the problem here is somebody had observed the credentials and they are replaying it later on. I don't want that to happen. So how can I prevent that? The way I prevent that is, I say every attempt at authentication should be unique. Whatever you use for authentication now, you come back tomorrow, we will use something else. And so that's the key thing. And how is it done? It is done by using something called a nonce. So a nonce is something which is a number, a random number, you use only once in your whole life. But this is a number, so this is only, it will be only, let's say 8 bits, 64 bits, 128 bits. So you can say, at some point you'll have to repeat it, because you only have a finite number of choices. But for all practical purposes, hopefully, the number is so large that you'll never repeat it. So now let's see how this protocol will work. Let's say Alice wants to authenticate with Bob. Right? So she says, I'm Alice. And let's say we are doing symmetric key here, so they share a key. Now what Bob will say, okay, fine, you are saying you're Alice, let me challenge you. Right? Let me give you a challenge. And the challenge is, I will give you a random number R, which is a nonce. And this will only be used now. Next time you come in, I'll give you a different number. And Alice's job is to encrypt this number. Okay? So Alice looks. Alright, that's something wrong with this. Anyway, so let's go here. So I'm Alice. You get a random number R. And what Alice has to do is, she has to encrypt this number using their shared key and send it back. And Bob will now decrypt it. And he will get R back. And he says, okay, I sent this challenge and I got the same thing back. So whoever I gave the challenge to, that person was able to encrypt it with the key that I was expecting. So it must be Alice. Because this KS, I only share with Alice. This key is only with Alice. So now let's see what happens if Trudy is there. Right? So in our attack scenario, Trudy was sitting there and then she was listening on and she could replay. So if Trudy is somewhere here, let's say, she's observing this message, she's observing this message, she's observing this message. She knows all of this. So she can replay this. Right? So let's say after some time, Trudy now wants to pretend to be Alice. So she will come back, she will go to Bob. Say, I'm Alice. Bob will say, fine, you are Alice. Let's give you a challenge. This time, some other number, R prime. Not the same. Now Trudy has to encrypt this. But Trudy doesn't have this shared key. This shared key is only with Alice, so she can't encrypt it. All she can do is she can play back whatever she had heard before. Right? That's the best she can do. Case of R. And Bob will decrypt this. This will come out to be R, and this is not equal to the challenge that he had sent. So it doesn't work. Authentication will be denied. And this is really what happens in most of our things, like for example, so let's say you have a Wi-Fi network at home, or in your office or wherever. Whenever you turn on your phone or your laptop to log into the Wi-Fi network, you already have a key stored in your thing, right? Whatever Wi-Fi access password or key, that thing. But you send the password, you actually get a nonce back. That's what Wi-Fi does. You'll get a nonce back, you'll have to encrypt it with your key and send it back. Because if I'm standing outside your home listening on to whatever Wi-Fi packets you're sending, I can listen on to everything. So Wi-Fi uses nonce. Most authentication protocols use nonces. And this one I showed with symmetric key. You can do the same thing with public key cryptography also. Again, if somebody wants to say, I'm Alice, Bob will give a challenge back. And now you have to encrypt it. How do you encrypt it? Using your private key. So how will Bob know that Alice has encrypted it? Bob will use Alice's public key. Now this comes up with an interesting thing. When we were doing our public key cryptography discussion before, we said that if you want to encrypt something, let me erase, if I go that far, the feedback picks up and then some sound. I take the message, I encrypt with the public key, and then you decrypt with the private. We are doing the opposite operation here. I do the encryption with the private key first, and then the public key, decryption with the public key. But the way those formulas are doesn't matter. Whether you use the public key to encrypt and private to decrypt, or the other, both will work. So in this case, Bob wants Alice to prove that she's the one encrypting. So she says you encrypt with your private key. How do I know it's Alice? I use Alice's public key to decrypt. What if I use somebody else's public key? It wouldn't work, right? For example, if Alice has encrypted this message, and I try to apply Bob's public key here, doesn't work. This will work only if you apply Alice's key. And in another way, as we'll see later, this can also be used for providing digital signatures. You know, when we sign something, when you sign a check, you put your signature on there, right? But how do you sign documents on the internet? Using something like this. We'll see that. And this is the relationship. Only public key and private key, which are a pair, can encrypt and decrypt each other. So if somebody has encrypted using this, that means it must be Alice, because only Alice has this. Right? Nobody else can sign it. Okay. So that's authentication. So now let's come to the last one, which is message integrity. Okay. And again, in integrity, what I want is, if I'm sending a message to you, it should go without any modification. Or if somebody has modified it, you should be able to find it out that somebody has modified it. And two things we'll look at there. One thing is, you want to look at digital signatures. If somebody is sending something, I want to be able to say that, okay, this message was definitely sent by Bob, or this message was definitely sent by Alice. So if sometime later they say, no, I didn't send this, you can take them to court and prove this message was definitely sent by Alice or Bob because it has been signed by their private key, something like that. And what we want to do is, so first thing coming with digital signatures, when Bob signs a document, we know that he is the creator of those documents, and this signature should be verifiable. So I could be able to go and say, okay, this is definitely Bob's signature. And it should not be forgeable, so nobody else should be able to create that signature. If I do that, then I say that, okay, this is definitely created by Bob. So let's see how we can do this. So let's say Alice wants to send a message to Bob. Sorry, Bob wants to send a message to Alice. And he wants to put his signature on that message. What can we do? Now don't worry about the computational complexity part. Of course, this is not very practical, and you will see that later, but theoretically it works. So Bob has this message M. What he will do is, he will encrypt the entire message with his private key. And what do I send? I send the message and the encrypted version of the message. Now I'm not worried about confidentiality, I don't care. It's like when you have a, what do you call it? A deed for a land sale, right? You have a property, right? So you have signature there. Everybody can read it, but there should be a signature there that it's yours, right? Or will when somebody's old, whatever it is. So in this case, Bob doesn't care what the message says. Let everybody know. All he cares in this particular thing when we're talking digital signatures is, it is signed by Bob. So I will send the message in plain text and an encrypted version of the message. So at the receiving side, what I will do is, I will apply, the pluses and minuses are gone from here, but anyway. At the receiving side, I will apply Bob's public key here. Right? So at the receiving side, what do I have? So at the sending side, this is what is happening. We have taken the message. We apply the private key. What do we get? Message. And we take this and we send it out. This is what we are sending. So at the receiving side, this is what we will get, right? These two things. What I will do is I will split it. This is the plain text message, and this is the encrypted message. And I will apply Bob's public key here. What will I get? M out. And then I have the plain text version. And I will compare. Are these two the same? If these two are the same, then I have done something. What have I done? I have done this. I have verified that Bob has signed it. And no one else but Bob. Why no one else but Bob? Because this thing was encrypted using this. If it was encrypted using any other key, this wouldn't have worked. And who has this key? Only Bob has this key. Bob can of course go and say, my key was stolen. Right? That's a different matter. But only Bob could have signed this, right? So I know that Bob has signed and nobody else, because nobody else knows this private key. And I can also say that the message that Bob signed was M, not some other message, because these are the ones that match. It's not M prime equals M. I know exactly what you signed. So later on you cannot come and say, no, I sent you a different message. I'll show you what you actually sent. Questions? Minutes. All right. Yeah.
Aren't these digital signatures prone to, cloning or copying or recording that you told us earlier?
Yes, but here I don't care about those things. It is a public document, which I just want to say that you created it. If you want to keep it confidential, then it's a different matter. Then we have to put encryption, there's some other kind of thing on top of it. At this point, I'm trying to say that this message was created by Bob. Let the whole world know what the message is. There could be some scenarios where I still want to maintain confidentiality. So for example, let's say I send an email to you. I want you to know that I'm the one who sent it. So I should have a signature. But the message should also be confidential. Nobody else should know. So we can build that on top of this too. But at this point, I have not considered confidentiality. This is just how do we attach a signature. So now, this thing works, but there's one practical problem. And the practical problem is this. I said you take the message and you encrypt it. Right? And before the break, we were saying, you cannot really encrypt this big message because it's computational too complicated. So this doesn't work in real life. If you have a 500-page document, it will be a very, very big message. You really cannot encrypt it too much. So what do? The way we do it is we use something called a hash function. Are you familiar with hash functions? All right, so you know hash function, right? But just in case, just a quick thing. What a hash function does is you can give it a message of any arbitrary size in general, a very large message. And what it will do is it will create a smaller version of it, usually 128 bits, 256 bits, whatever it is. You give any message, you will get a smaller version, smaller message out. Any size input, fixed size output. And what we are going from is from a large message to a small message, right? So this could be 5,000 bits, this is 100 bits, 128 bits. So what you can imagine is, it's a many to one. There will be overlap. There will be overlap. Many messages can get mapped to the same number. But hopefully, if you keep the number of bits in the hash output large enough, right? If it's a 128-bit hash, it's 2 to the power of 128 possibilities. Do you have 2 to the power of 128 messages that you want to distinguish between? Most cases, probably not. So while it's a many to one, and it is possible that two numbers will map to the same hash output, hopefully that doesn't happen, or doesn't happen very often. And of course, if we go from 128 to 256 bits, the likelihood of that happening will be even smaller. Right? So for all practical purposes, what we will assume is, you give something as the input, you will sort of get a unique output here. But it is much smaller and of fixed size. Right? So it's a many to one function, and it will produce a fixed size output, which is also called the digest or the fingerprint. Okay? And now we are in a position to figure out what we need to do. So let's come here. So earlier what I did is, I took the message and I tried to encrypt it, and then send the encrypted version and the original message. This works, but this encryption of a large message will be prohibitive. So instead of that, I do something else. I take the message, but I first pass it through a hash function. So here what I have is the hash of my message. This may have been a 1 GB or whatever it is. Let's say it's an email. So let's say this is 1 megabits. What I get here is 128 bits. And then I encrypt this 128-bit number. So I encrypt the hash of my message. And what I send out is encrypted version of the hash of the message. So this is practical. Running through a hash is very easy, and then encrypting a small number is possible. That's not a problem. And on the receiver side then, before I do this, I have to do something else. I have a hash of n, right? And what I will get here is hash of m. And on the receiving side, what I have is I get the message. I only have the hash of the message. So I cannot compare the messages directly anymore. So I pass it through the same hash function. And what I get as the output is the hash of this. And then I compare. Are you saying? So effectively, I have done the same thing that I was doing before, but in a computationally much more practical way. So here also, after all this, I know that this hash was signed by Bob because I use Bob's public key here. So this hash, this thing was signed by Bob definitely because nobody else has this. And I also know that this is the message they signed, just like before. You could always say that, maybe it was some other message and by chance the hash output was the same. The code is not going to buy that. The likelihood of that is very, very small. Questions? All right. Oops, something has gone wrong with my animations today. So what about these hash functions? What kind of hash functions do we need to use? There are some well-known hash functions which you can use, right? And the most common ones are MD5 and SHA-1. MD5 will produce 128-bit message outputs, and SHA-1 will give you 160 bits. Now, of course, you will see that this is more sorry, this is more secure than this, right? 160 bits and 128 bits. If I were an attacker, what would I have to do? If I were an attacker, I know that, let's say this is the hash output, right? If I was modifying the messages, what I want is, I want to modify the message in such a way that the output of the hash would still be the same. Then my attack is successful. It's much easier to do that with 128 bits than with 160 bits, because with 160 bits, the inputs, it's much more larger. So what is good enough? Should we use this? Should we use this? Of course, this has more complexity, and you are sending more information, so overhead is higher here. In general, what we think, so if you're doing banking and other things, of course you go for this. For IoT, the understanding is that 64 bits is okay. If you have a 64-bit hash, it's okay. Not very sensitive IoT data. A reasonably sensitive thing, which even if it gets leaked, it's not a very, very big deal. About 64 bits would be okay. And the reason is then, if you go for a smaller hash, the energy you will spend, the computations you have to do will be lower. So you will save on that. So, okay. And the last thing is operational security, where we talk about intrusion detection systems and firewalls. Right? So this is a castle, and the job of a firewall is to keep bad people out. So you have a network. The job of the firewall. So one of the things you want to protect your network is by preventing people you don't want from getting in. Right? Somebody is launching a denial of service attack on you. You don't want those packets to reach your network in the first place. How do you keep them out? You use a firewall. And in the old days, this is what we had, right? So this is, let's say, my network. There's only one way to get in. And I have guards here who will check each and every one and see if you're eligible to come in or not. Right? And that's what a firewall really does. It will isolate an organization's internal network from the rest of the internet. You will allow some things to come in, and you will block them. Which ones do you allow and which ones do you block? You decide. Depends on your policy. What do you want people from your network to access? What are the things inside your network that you want outsiders to access? So for example, in a university like this, you will allow outside people to access your web server. Right? If they want to access BHU's or IIT-BHU's website, they should be able to come in. But if I have some computers in my lab here, I don't necessarily want outsiders to be able to connect to my computers in the lab where I'm writing my thesis. Right? So there could be different rules and so on. Similarly, email. I want to receive emails. So people outside should be able to connect to my mail server. So you could have different kind of rules. You could also say, my students, they're wasting time looking at Facebook, right? Or whatever, looking YouTube videos. So I can block HTTP traffic going out, something like that. Right? Or I could block some specific websites. They're all rules of the firewall. The biggest and the most complicated firewall in the world, the Chinese government. Not joking, they have the most, if you're in China, for example, you cannot access Gmail. You cannot access many of the Western news websites. You cannot, Google, you cannot, and Google Maps is not there. All Google services are not there. You cannot do Facebook, and so on and so forth. So these are some of the reasons which we already sort of talked about, why we would want firewalls. One of the bigger things is to prevent denial of service attacks. So I want to make sure whatever is coming in is real traffic, not fake things. And then I don't want people to come in and modify my internal data, so I want to prevent access to my sensitive stuff. Only authorized people should be able to come in. If you're a business organization, you'll be very, very sensitive about it. Right? If you're Apple, you don't want Samsung to come in and sniff around in your network to see what's going on. Right? And usually there are three types of firewalls, something called stateless packet filters. There are stateful packet filters and something application gateways. So this is not very interesting from the IoT perspective, so I don't think I have it here, but I can talk about it if you want. So let's look at these things, right? So stateful and stateless packet filter. So what this firewall is doing is, it's sitting on your gateway or the router which connects your network to the outside world. In a campus like this would probably be somewhere in the computer center. So this is the router which connects IIT-BHU to the outside world. Here I have a firewall. So a firewall is nothing but a computer again. Right? It looks at every packet coming in and every packet going out. And it decides, what should I do with this packet? Should I let it go or should I drop it? Right? In case of a stateless packet filter, each packet is treated independently. I don't care what happened in the past. New packet comes in, I just look at this. I don't care about anything else. Is this packet good enough? I don't care about any ongoing connections and other things. If this packet satisfies my rules, then I let it in. If it doesn't, I drop it. Right? So it does packet by packet. It looks every packet individually and so on. So what should I look at in order to decide? The common things are, you can look at the source and the destination IP addresses, for example. You could look at what are the port numbers they're trying to access. You could look at, what kind of management messages. Sometimes they're ping packets, for example, right? A ping is a ICMP message. Trace route is an ICMP application, right? Sometimes we want to allow them, sometimes we don't want to allow them. So you could decide on that. You could go deeper. Instead of just looking at the source and destination IP addresses, you could start looking at various fields in the headers. So if it's a TCP packet, I could see, is it a TCP SYN packet? Is it an ACK packet? And things like that. So now, are these sufficient? Should I be looking at something else? Most of the time, these rules are set by the administrator based on his or her experience. Right? Based on whatever they have figured out in the past, then they do it. And as things become more complicated, you have more devices, sometimes we don't know everything, right? So that's where your machine learning sort of comes in. How do I set these rules? What should I be looking for? You could potentially automate things or come up with better things to look for if, for example, you use machine learning. That's one of the, I said I'll try to motivate getting into machine learning over the next, not tomorrow maybe, but after that. This is one of the things. So now let's look at what kind of things. How do we set these rules? Let's take an example. If I have a rule that says any packet that comes in, okay, and I'm looking at the header of the IP packet, if the IP protocol field is 17 and either the source port is 23 or the destination port is 23, then block it. I could have a rule like that. So then you have to think, what does it mean? You have to know what these fields mean really. And IP protocol fields, so yesterday when we were doing layers, so IP is a network layer protocol here, right? So this is IP. And on top, you have the transport. So this is network. Oh crap, I don't have space. Transport, okay, I don't have space. Now when an IP packet comes in, it has to go to the upper layer now, to the transport layer. At the transport layer, for example, I have two options. Not UDP, correct. Which one should I give it to? That's the IP protocol field. If it is 17, it goes to UDP.
Connectionless and connection oriented.
That's correct. Yeah. And This IP protocol field says, should it go to UDP or to TCP? In this example, it says, if it is 17, that means it's UDP. So I'm going to drop it. Yes.
These are actually well defined, I think, for fields.
Sorry? These are well defined.
Well defined.
They're very well defined. So if you just look up the RFC, request for comments, as we call the standards, if you look up the RFC, or pick up any textbook on computer networks, you will know what these fields are, but just as an example. Right? So, and the port number. Port number sort of says what application it has to go to. And port number 23 is for an application called Telnet. It's for remote login. Right? You want to log into a computer somewhere else, you use Telnet. And back in the day, so for example, 20, 21 years ago, when I was a student, we used Telnet. We don't use Telnet anymore. Why? Because in Telnet, when you do Telnet to a host, it will say, what is your username? What is your password? You type that, it goes on the network. It's not encrypted. So if somebody else is sitting on the network and looking at all the packets, they know what the password is and what the ID, what the username is. So Telnet is not used anymore. It has been replaced with something, for example, SSH, Secure Shell, where everything is encrypted. So most network administrators now will disable Telnet. If I see anything going to Telnet, no, not going to happen. So this is what it does. It blocks all UDP flows and Telnet connections. We could also do something else. So if there is any packet which is coming into my network and the ACK is set to 0, ACK bit is set to 0, I discard it. Why? Because this belongs to something, a flow which is not there. Somebody is trying to establish a flow. You remember we did this in the morning today? I drew the three-way handshake for TCP. First we have to send a SYN packet. Ah, crap. I keep doing SYN packet. Then I get a SYN plus ACK in response. And then I send an ACK. So what does it mean, ACK? All it says is this is an acknowledgement packet, but how do I indicate it's an acknowledgement packet? In the TCP header, there is one bit to say if it is an ACK packet or not. So I just set that bit to be 1. Here, I will set that bit to be 1. This is a SYN packet. This is, I'm trying to establish a connection. I'm not acknowledging anything yet. This packet was acknowledging this previous SYN. This is the first SYN that's being sent out, first thing. It's not acknowledging anything. So there is also an ACK bit here in the packet. The header has an ACK bit. It's just that it's set to 0. So we don't, when I write, I just say SYN. So a TCP packet with an ACK bit of 0 is the first SYN packet. Everything else in the whole conversation will have the ACK bit set to 1. It will always ACK the previously received data packet, the last received data packet. Even if you send data here now, let's say, right? You are sending data, you're not sending anything else, right? But here, ACK will be 1. Why? You are you're repeating this ACK. You always ACK. So TCP has cumulative acknowledgement. So let's not get into the details of TCP. All we want to understand is, in a TCP connection, only the first packet has an ACK bit of 0. And if I don't want anybody to get into my network, I don't allow any TCP connections. I don't want anybody to come in. I'm mean. Right? I look for these packets. This packet means somebody is trying to make a connection in my network using TCP. I don't care whether it's a web connection or an email or FTP or whatever it is. I don't care. I don't want you. So what this will do is, it will prevent all external clients from making a TCP connection into my network. And then we could have different other things. So for example, if my policy is, I don't want my own people to access websites outside. What I can do is, I know websites, if you're trying to access a web service, you're going to use HTTP, right? You're going to access a web server. The port number associated with HTTP is always 80. So if I see you're trying to send something to some server at port 80, I know you're trying to connect to a web server. So I will stop this packet from leaving my network, so you cannot connect outside. Similarly, if I don't want, so now let's say I'm going to be more generous. Here I was dropping all incoming TCP connections. No matter what you want, I drop you. But let's say I'll be a little bit more reasonable. And I'll say, okay, you cannot connect anything except for my web service. You can come into my network only if you're trying to connect to my web server. So in this case, I will drop all TCP SYN packets and accept my web server. Let's say this is my web service IP, and you're connecting to port number 80 of that machine. Anything else, I just drop. If you see that too many people are listening to the music or watching streaming videos and so on transmitted over UDP, that's clogging up your network, what you can do is you can drop all UDP packets. So you can look at the it's not here. You can look at a protocol field of 17 and you drop every UDP packet. And so on. And the way it's usually implemented is inside your firewall, you would have a list like this. This is called an ACL or access control list. If you're the system administrator, it's your job to set this up. And it will have entries like, what's the action? Do you allow or deny? Those are the only two actions. And for example, let's look at this. What I want is no outside, or which one am I going? Right. So let's say what I want to, let's say what I want to do is I want to implement this policy. This is like a high level policy, right? This is what I have decided. I want to allow only website connections. And I know that this is the way to do it. How will I actually implement it in a firewall? Like this. What I will say is, so this is my network. And this is outside my network. So if there is a packet starting from my network and it's going outside my network and you're using TCP and you're going to a web server, I'm allowing it. Okay. Also, if somebody from outside is trying to come in, so the source address is outside my network and it is coming inside my network and it is trying to connect to my web server. And it's coming from a web server, it's coming from a web server, then I allow it. If I do this, then I'm allowing people to access websites outside. And in this case, you see, I'm allowing UDP, but at port number 53. So port number 53 is the DNS, which allows you to translate names into IP address. If you're talking about initially, we're talking the DNS server, denial of service attack on DNS. Right? So when I have this, this allows all the DNS. So now you can figure out what policies you want to implement. Then you figure out to implement that particular policy, what's the firewall setting you need. And then you code it up into your firewall settings. And as long as these are matched, you'll allow everything else you just deny. Now, that one was stateless. So I just look at each packet individually. Right? Sometimes that can get me into trouble. Right? So if you look at the previous one, I had this thing, this line. This line says, if somebody from outside sends me a packet to something inside my network, this is a TCP packet, and it's claiming that it's coming from a web server, and it's going to some port number in my network, and the flag bit is set as ACK. Then I allow it. This could be a loophole. Why? Because somebody could start launching a denial of service attack on me. What could happen is, so let's say this is outside, and this is my some computer. This is my server in my lab. Somebody wants to launch a denial of service attack on my lab computer. What they could do is they could just send packets randomly. Doesn't matter what the source address is. It's coming from outside and it is coming to my server's address. Let's say 222.22.2.2. So a packet comes in saying it wants to go to 222.22.2.2. Some port number, let's say 5076. So this is coming to my computer here. Where is it coming from? Somewhere outside. Let's say 128, 113, 16, 5. And the source port is 80. So this says it's coming from a web server. And the ACK bit is 1. My firewall will let this packet inside. Did I start a connection with this web server? I didn't. Somebody is just randomly sending me packets like this. It will get in my network and it will come to my server here, and then depending upon what my server does to these packets, either it will waste time trying to process that packet. Maybe it will throw away the packet, but at least it has to process, look up saying, do I have an ongoing connection? No, so I'll throw this, but it will waste resources. Denial of service. So in stateful, what we do is, for every connection that is going on, for every TCP connection that is going on, I have to store it in a table. Right? So, for example, let me delete this guy. Let's say this is my network, this is my firewall, and this is outside. So let's say this host, 128.113.16.5. Let's say at some point it started a connection outside. Send. When my firewall sees that I'm trying to establish a connection outside, it will allow it to go. When it goes and comes back with a SYN plus ACK, what does it do? So let me step back. This hasn't come in. So somebody from inside my network sends a SYN packet outside. What this firewall has to do is, it has a table which says source, destination, port, port. It will say 128.113.16.5. Tried to establish a connection with, let's say 143.6.2.1 and whatever port numbers are there. It will maintain a table like this. So you send a SYN, connection has not been established yet, but I know that somebody from inside is trying to establish a connection. Now when the SYN plus ACK comes back, before I let it inside, I will first check this table. Did somebody from inside actually try to connect outside? If yes, then I will let it in. So this is stateful. So I'm keeping track of what is the state of my network, which is sort of saying, I'm keeping track of what connections I'm making, or my people are making. So I just don't look at the packet itself, I look at the history. Was a connection happening? If it is made, then, and that is what this table says. If something from outside is coming, from something inside, and it is claiming to come from a web server. It's all fine. I will let it in, but I have to check connection now. Is there an existing connection with that web server between these two guys? If there is an existing connection, fine. If not, go. Thanks, and so on. And this is stateful. One of the limitations of firewalls is that you are checking all these IP addresses and so on. Sometimes you don't know if it really comes from this. I can always spoof IP addresses. So if you have a table which is based on these IP addresses and so on, sometimes I can just pretend. That's one problem. Also, it doesn't work for what is called zero-day attacks. These are attacks I know people could possibly attack like this. But do I know everything that is possible? I don't know. Maybe tomorrow you'll find a new way to attack things. That new way of attacking things is not in this table. So your firewall doesn't help in that case. Right? And usually in many cases for UDP, it's binary most of the time. Either you allow UDP or you don't allow UDP. Sometimes that's a bit restrictive. All UDP is not bad. Right? Sometimes UDP can be good too. And then again, there's a trade-off in this whole thing. By using all of these policies and so on in a firewall, what I'm doing is, I'm sort of restricting access, either to the outside world or for the outside world to come in. When will I be most secure? When everything is denied. You cannot go in, nobody can come in, everything is secure. Right? But then what's the point of having a network? And it defeats the purpose of connecting things. Right? So there's always you want to be more secure, restrict more things. You want to be less secure, allow more things and so on. Right? And everybody has firewalls and so on, and attackers still find ways of figuring out how to get in. So, you can always question how effective these are, but it's definitely better than not having anything else. All right, so last thing is quickly on intrusion detection system. So in the firewall, what we do is, we are only looking at the headers. We only look at the IP and the TCP or the UDP headers, all kinds of fields, the addresses, port numbers, sequence numbers, and so on, and then we try to decide what to do. We don't look at what data it is carrying. So the headers are there, I look at that, but what's inside? Are you carrying a virus? Firewall doesn't look at that. What looks at that is something called an intrusion detection system. Right? So packet filtering only operates on the headers and so on. In this case, we look at what's inside the packet, which is called deep packet inspection. We look at every byte of the packet. And then I try to see, okay, is this sequence of bytes that you're carrying, is it a virus? Is it not a virus?
So like mail server, kind of like using the Gmail and attaching some exe files. So I think this kind
that is, yeah, that's similar thing here, right? So when your antivirus says your exe file has a virus in it, that's sort of what it has done. It's just that in this case, it's happening before the mail even reaches the mail server. I'm doing it in the network itself. Mail servers do it. I have an antivirus on my computer. That also same principle sort of thing. And then it can also look at not just one packet. I can look at what's happening over the last 3 minutes, or 5 minutes, or 10 minutes. Am I getting too many packets from one particular host? I've never seen this host connect to my computer before. But all of a sudden this comes in and it is sending me directly a lot of traffic. That could be an anomalous behavior. And these are all things where, things like machine learning, artificial intelligence, and things which can help. Here we are trying to figure out things which, I've not necessarily seen before. I have seen something, but it's not necessary that I have seen everything. But can I use my previous knowledge to somehow classify now? Whatever is going on in the network now, is this okay or is it not okay? And even trying to figure out these rules here, what to allow and what not to allow. You could make it a look. In this case, the rule is very simple. If port number is this, IP address is this, then this. You're checking two conditions. You could have a decision tree which is much longer. If this is happening, it's middle of the night. Many times you don't expect certain, at the middle of the night traffic should go down. So you could have more and more conditions. If this port, time of the day is this, and there are 5 other connections going on, so you could have much more complicated ways of figuring out what should be your rules. And that again brings us to machine learning, which is a field called decision trees. And we will look at that, I think, day after tomorrow. So hopefully we are going in that direction. Right. So I think we will stop here for today, but what I have is something specific to IoT and so on. I don't know, but these are much more researchy things, and how many of you are even interested in this? 1, 2, 3, 4, all right, half roughly. So I'm going to toss a coin tonight and then we'll decide whether we do this. So that I think will make reasonable. So thanks for coming, and I'll see you tomorrow then, unless you have questions.
Sir, is there any reason to take a port as port 80?
So port 80 is defined in the standards for web server. So if you're running a web server, you have to run it on port 80. So you cannot change it. You could change it, but then nobody else would be able to connect to your web server. So whenever I want to connect to Amazon.com, Flipkart, it's port 80. And that's defined by the standard, so you don't change it. All right, I'll see you tomorrow then. Watermark is a special way of doing a digital signature. So digital signature basically says if somebody has changed something, you want to know. That's one way. Well, I wouldn't say digital. So digital signature is here. It says you are the one who created it. It does say that. The only difference really is when you use a digital signature, it's always extra part. In most watermarking things, then it's nothing different than a signature. Fundamentally.